So this is Math 2020, lecture number 44, in which we will cover sections 9.1 and 9.3 from the text. We're going to do this, we're going to cover this material. We're going to cover the material in sections 9.1 and 9.3 rather summarily. What I mean to say is that if we substitute for 1 minus p over m 1, then we get back the exponential growth model. Okay, so this carrying capacity has to do with the fact that you may have limited resources for which population can grow unfettered. A solution to a differential equation is a function that satisfies the equation. By the way, if we assume a fixed value of the initial population in this example, it's called an initial value problem. Okay, so by the way, exponential decay is, I said the case k is less than 0, and this equation models things like half-life of radioactive isotopes. Okay, so let's take an example. Suppose we have exponential growth, dp dt, equals twice p. I want to show you, let's check that p of t equals e to the 2t is a solution to this equation. Well, how do you check it? So dp dt, if this is our candidate solution, by taking the derivative of e to the 2t, you get twice e to the 2t. But if p of t is e to the 2t, this is twice p, so this equation checks out, the original equation checks out. So this is a solution. So this is a solution, okay? But there are other solutions. There's not a unique solution. For example, we can take p of t equal to a constant times e to the 2t, see any constant, and that will also satisfy the equation. So there's not a unique solution to a differential equation typically. Solutions come in families. Here, the family is completely determined by the constant c so there, for every real number you get a different solution. Okay, so so that's the example. So let's actually now try to solve let's do some solutions to the exponential equation. Okay, so solving the exponential growth equation. So we have dp dt equals k times p. What we can do is divide both sides of the equation by p and multiply both sides by dt. So that leads to dp over p is equal to k times dt. And now we can integrate both sides. And what does that give us? The integral of dp over p is equal to the integral of k dt. But that the integral of the left side is ln, and I don't have to put an absolute value in here because p is population. We're interpreting it as population. Population is never negative. So ln of p is equal to the constant times t plus, say, c. Now, we can solve for p by exponentiating both sides. We get e to the ln of p, which is p, is equal to e to the kt plus c, which we can think as e to the c times e to the kt. And that leads to the final solution, p equals a e to the kt, where we've used the fact that e to the c is equal to a. So this is the general solution of the exponential growth or decay equation. There's more to say about this, though, because if I take p equals a e to the kt and substitute in p of 0, that's going to be a e to the k times 0, so that's a, but p of 0 is the initial population, so we could have written this instead as p equals p0 e to the kt. So that's the complete solution to the exponential growth equation with the initial value p of 0 is p sub 0. So let's do an example. So here's an example. Suppose we have an initial population of 100 bacteria in a petri dish, and we assume exponential growth. And after one day, oops, that's not right, not 100, one day. So after one day, the population grows to 300 bacteria. Okay, so the question is, after how many days are there at least 10,000 bacteria in the petri dish? And again, I'm assuming an exponential growth model. So we know that p of 0 is 100. That's given to us. This is the solution. So we get p of t equals 100 e to the kt. We have to first of all solve for k, but we're given an additional piece of information that p of 1, we're assuming that t is measured in days. P of 1 is, we're assuming 300, and that's equal to 100 according to the equation e to 3k, e to the 3k. So that tells us we can solve for k from this. We get e to the 3k equals 300 over 100, which is 3. So ln of e to the 3k is ln of 3. So 3k is ln of 3. K is 1/3 ln of 3. So that's right. Okay. So then we can use our calculator to figure out what ln of 3 over 3 is, and it's approximately equal to 0.366, close enough. And therefore, we see that P of t is equal to 100 e to the 0.366 times t. Okay, so that tells us what the equation is. Now we have to figure out the solution to the problem. When do we have at least 10,000 bacteria? So we want P of t to be greater than or equal to 10,000. So that means we want 100 e to the 0.366 t to be greater than or equal to 10,000, which means that e to the 0.366 t is at least 100. taking ln of both sides does not change the inequality, so you get 0.366 t is greater than or equal to ln of 100. This is very messy, so I'll rewrite it. And then we divide by 0.366, we'll get t is at least, what is t? If you solve the equation, you'll get the inequality, you'll get ln of 100 over 0.366. And that is 12.58 approximately, so that's days, and that solves the problem. T should be at least 12.58 days. So if we're just looking at units of days alone, integers, at least 13 days. Okay, so that's the solution to our problem here. Okay, so not all solutions to differential equations, not all solutions to a differential equation are explicit, meaning they're not all functions, they're actually curves. So here's an example. dy dx equals minus x over y. Okay. In fact, we can completely solve this equation, and this comes about, this is actually more like the next section, but we can separate the variables. We get y times dy equals minus x times dx. We can integrate both sides, and we get y squared over 2 dy, oops, no dy there, y squared over 2 equals negative x squared over 2, and then we can put a c in. In other words, x squared plus y squared equals maybe some other constant a. I've gotten, let me actually say how I got this. So x squared over 2 plus y squared over 2 equals c. We can multiply both sides by 2. We'll get x squared plus y squared is 2c, but I'm going to call 2ca. So this is a circle if a is positive. All the solutions are circle of radius the square root of a. So every solution has the form of a circle of this equation. Here are all these circles, except when a is 0, you'll get a point, the origin, and then if a is negative, there is no solution. There is no such solution. But notice that none of the solutions are actually functions because these are curves which don't satisfy the vertical line test. So sometimes the solutions, which in this case form a family again, for each value of a, you get a solution as long as a is not negative. You'll see that you don't get a function necessarily. Okay, this leads into the next section, which is section 9.3, which is how to solve separable equations. So the idea of a separable equation, we've only been dealing with them actually so far, is that it's an equation that could be written, it's a function in one derivative, and you can write the equation in this form, g of x times h of y, where g and h are functions. So how do you solve this? So what you do is you separate the variables, meaning we get everything involving y on one side and everything involving x on the other side. And now you integrate both sides. And if you're lucky, you can integrate these functions. But once you integrate them, you have the solution. at least in implicit form. Okay, so I thought I'd look at an example of the logistical equation, the logistical population growth equation. Okay, so I had to go and check on the bread. So anyway, I want to consider a special case of the logistical equation in my next example. So let's consider the case where the carrying capacity is 1. So let's look at the case dP dt equals P times 1 minus P. So here, this is a special case of the logistical equation where the constant K is equal to 1 and M is also equal to the carrying capacity is 1. So how do we solve this? Well, this is separable. We look at dP over P times 1 minus P equals dt. Okay, and now we have the left-hand side is gonna, when we integrate it, it's gonna be we're gonna wanna do partial fractions expansion. So it turns out that I'm gonna save you time and not actually derive the partial fractions. I'll just give you the answer. It's given by 1 over P plus 1 over 1 minus P. And that's actually correct. So we're going to get if we integrate, we're going to get on the left side the integral of dP over P plus the integral of dP over 1 minus P equals the integral of dt. Now, the integral of dP over P is ln of P. I'll put the absolute value in, but we're going to get rid of it later because P is not negative, remember. The integral of dP over 1 minus P is minus ln absolute value of 1 minus P. And the integral of dt is T plus some constant, let's call the constant C. Okay, so now we can rewrite all of this. I want to solve for P. So the first thing I can do is I can change all the signs. I'm going to multiply both signs by -1. It'll be convenient to do that. So if we think of this, multiply both sides of the equation by -1, we get ln of 1 minus P minus ln of absolute value of P is equal to negative T minus C. Okay, but the left side of this equation is ln of 1 minus P over P, absolute value, is equal to minus T minus C. Now we can exponentiate both sides. So we'll get 1 minus P over P absolute value is equal to e to the minus T minus C. And we can think of this right-hand side as e to the minus C times e to the minus T. And then we can think of e to the minus C. We can set a equal to e to the minus C, and we'll get a e to the minus T. Okay. Now, if P is between 0 and 1, we'll get 1 minus P over P. The inside the absolute value is not negative, and we'll get is equal to a e to the minus T. And what happens then, we can solve for P because we'll get 1 minus, by cross multiplying, we'll get 1 minus P equals P times a e to the minus T, or in other words, 1 equals P plus P a e to the minus T. We can factor out a P and divide by both sides. In other words, I'll factor out a P, you'll get 1 plus a e to the minus T. So P of T equals 1 over 1 plus a e to the minus t. That's if p is between 0 and 1. If p is greater than 1, you'll get something similar because in that case, p minus 1 over p is equal to a e to the minus t. But if we, I'm going to need more space for this, so let me deal with that case on the next slide. Okay, so what do we got? Okay, so if p is bigger than 1, then we'll get p minus 1 over p equals some constant a times e to the minus t. But we can multiply both sides by minus 1 in that case. We'll get 1 minus p over p equals minus a e to the minus t. And then we can define this as, we'll have a new constant, call it b e to the minus t, where b is equal to minus a, and then the solution looks exactly the same. P equals 1 over 1 plus b e to the minus t. So in both cases, we'll get p of t equals 1 over some 1 plus some constant a times e to the minus t. The only difference between the case p is bigger than 1 and the case p is less than 1 is in the p bigger than 1 case, the constant a, which is b, is going to be of a different sign. Okay, so this is the general solution. Now, what is the relationship between A and the initial population? So if you plug in t equals 0, we'll get P of 0, which we'll call P sub 0. If we stick it into the equation, we'll get 1 over 1 plus A. So therefore we can solve for A. A is always given by solving for it, 1 minus P0 over P0. That actually solves. So that's what A is always in terms of the initial population. Okay, we can actually study what these solutions look like. So let me do that in the upper left-hand corner here. There's not a lot of space, but so here we have the carrying capacity, which is 1, height 1. Now, what does this function look like for value? How does the graph of it look like? Well, we have, if P0, if the initial population is between 0 and 1, here's what happens. Then P of t remains between 0 and 1. You can see that. This function is actually increasing. As t goes to infinity, this term, which I'm circling now, is going to go to 0 as t goes to infinity. And so the function is increasing to 1, and it looks like this asymptotically. For t negative, it looks like this. Okay, so all of the solutions are increasing to the carrying capacity. In that case, in this particular case, if t is bigger than 1, if p is bigger than 1, the same thing is true, but it's going to be P0 will be bigger than 1, and the solutions look like this. Everything tends towards the carrying capacity. Notice that P equal 1 and P equal 0 are also solutions to the equation. These are constant solutions. They're called steady states. So this is actually a complete description of logistic population growth in a special case where the carrying capacity is 1. The general case is very similar, but I don't want to. I don't want to even illustrate it. I just want to indicate that the picture looks the same in that case. Okay, I think that's enough for today. This is a short lecture. We will continue next time.